Morning, everyone. I just want to say thank you for the opportunity to present at the fourth International Conference on Material Science and Nanotechnology. I am called Yankam Brenda, and the paper I'll be presenting is titled Robustness of Orthogonal Uniform Composite Design Against Missing Data. The line is going to run from the introduction right up to the acknowledgement. Introduction. So we'll start by defining what robustness is. Robustness is a characteristic that provides protection to a design against deviations from its usual assumptions so that that design performs well under certain conditions. Now, a design is said to be robust to missing values if that design is constructed under certain criteria and then perform well by other criteria. Missing values are actually are practical problems that occur in many experimental settings, and they can hardly be avoided even in a well-planned experiment. This missing value can significantly impact the statistical accuracy of an experiment as well as the estimates of the regression coefficients, thereby rendering an even well-planned experiment unsuccessful. The different researchers have developed techniques or criteria to treat these missing values, some of which include the case deletion technique, which consists of deleting the variables with the missing data and then analyzing the remaining data. Then we have the method of least square and also the probability of estimability criteria. However, this technique may not be a sufficient way to construct experimental designs that are robust to missing values. Hence, the use of the Minimax Loss criteria to construct robust experimental designs are preferred. So in this paper, we shall adopt the Minimax Loss criteria to construct a robust orthogonal uniform composite design, and this new design shall be called orthogonal uniform composite minimax loss design, that is OUCM. The aim for constructing the OUCM includes finding values of the known zero coordinates of the initial orthogonal uniform composite design points that minimizes the impact of the missing value. To the literature review, we'll see a few literature review, a few work. So let's take for instance Ahmad et al. 2012 that constructed a type of robust design called augmented pair minimax loss design, and this design was found to be robust to one missing value and more efficient compared to the initial augmented pair design of Morris 2000. The next one is that of Chen et al. 2017 that constructed robust orthogonal array composite design and called it orthogonal array composite minimax loss design, and it was found that this design was more robust to a missing value and also performed better in terms of the efficiency compared to the original orthogonal array composite design. Then Zhang et al. 2020 constructed a type of composite design called orthogonal uniform composite design, that is OUCD, to estimate the parameters of the second order model. And in this paper, we extended the work of Zhang et al. By constructing a robust design that is robust to missing value. Move to the model that is considered in this work, and because we are dealing with second order design, so the model we are going to be working with is the second order model as defined in equation 1, where our beta naught is the constant term, then beta I is the linear, beta II is a quadratic term, and beta ij is the interaction term. Then the parameters now of the second order model is defined as P equals to this, where K here represents the number of factors. Now let the determinants of the information matrix, that is D equals to these, such that the model matrix n by p corresponding to the parameters of the second order model is partitioned as this, where our first term is a constant term followed by the linear, quadratic, and then bilinear term as defined in equation. Next thing we are now going to look at is the Minimax Loss criteria, and this Minimax Loss criteria is the criteria that is going to be used to construct our robust design. So in order for us to use the Minimax Loss criteria, we will consider that W value is missing in a design. And if W value is missing in a design, then the model metric is reduced by W row. Now if the model metric, now let the model metric be partitioned as X, which is equal to this, where our XW represent the design with the missing value, and X arrow represent the reduced design. Obviously X transpose X is given as in equation 3. Now the relative reduction in the determinants of the information metric is called the loss, and the loss due to the J design point missing is defined in equation 4 as this, such that the loss function of the factorial axis and then center point are defined respectively in equation 6 to 8. Next, we'll be looking at how to construct our robust design, that is robust orthogonal uniform composite minimax loss design. The first step includes selecting first of all an initial design U, which is defined by this, where U1 represent the factorial portion, U2 represent the axial portion, and then U0 represent the center points. This design is without the missing value. And then let U star be given by this. So the next step, we calculate the loss functions of the factorial axial and then the center point by using equations 6, 7, and 8 based on U star for a missing value for the second order model. Then we now find the new alpha value that minimizes the maximum loss of the factorial axial and center point, and now substitute that new alpha value in U star such that an OUCM is what constructed. That is our robust design. So the next thing we'll be looking at is the design comparison, the criteria that we are going to use to compare this our robust design with other existing design. So the first criteria we'll look at is the relative D efficiency. And the relative D efficiency, according to Ahmad et al. And Chen et al. Of design B to design A, is the ratio of the separate D efficiencies as defined in equation 9 by this, where our B here represent the design with missing value, and then A represent the design without missing value, and P is the number of parameters under study. And according to Ahmad et al. 2012 and Chen et al. 2017, the relative D efficiency of design B to design A greater than 1 is often desired, as it indicates good performance. So the next criteria is the generalized scale deviation. And this generalized scale, the generalized scale deviation is a criteria that aids in estimating a subset of model parameters in terms of precisions. That is, it estimates both that of the linear, quadratic, bilinear, and even bilinear terms, and also the constant term. Chen et al. 2017. The smaller the generalized scale deviation, the better the design. So we see from equation 10 to 13 the different, that is equation 10 represent the generalized scale deviation for the constant term, then 11 to 13 represent that of the linear, quadratic, and then cubic term. The data that is used to construct our robust design, that is robust OUCM. And here we see that following the structure, that is following the structure of the orthogonal uniform composite design, that is OUCD, that which is composed of 3 portions. We have the factorial portion, the axial portion, and then the center points. So table 1 here gives us the 2-level factorial portion and the 3-level uniform design for different K factors, that's factor 2 to factor 11. You see the different structure here. So the OUCMs are then constructed based on the structure of the OUCD by following the step that has been outlined already previously. And now table 2 here gives us a general structure of a 30 runs OUCD, that is for factor 4, with N0 equals to 5 center points. So we see the factorial portion, the structure of the factorial portion, we see that of the axial portion, which is the uniform design, and then we see the center points, which are 5 center points. Now we move to the analysis and the results of the OUCM. So We should know that the loss function or loss structure of the factorial area and the center points were obtained by using the equation 6 to 8, and based on the values that were obtained for it, we then have this result presented in table 3. So table 3 gives the different loss structure of the OUCD for factor 4 against the different alpha values using n not equal to 5 center points. And from this table, we observe that as the loss of the factorial is decreasing, that of the axial is increasing, while that of the center point has like a bell shape. So now moving on to figure 1, that is, this data in table 3 was represented graphically in figure 1, and from this figure 1 we then extrapolate it down, and then we obtain now the new alpha value, and that new alpha value is the alpha value that is now used to construct the OUCM. So we should note that different new alpha values were obtained for factors 2 to for factor 4 for factor 4 to factor 11, and these different new alpha values were now used to construct the OUC, the different OUC. So table 4 here now represents the different alpha values. The different alpha values are presented above, that's without the bracket, while the values of the relative Z efficiency are presented in bracket. So from this table 4, we observe that the OUCM have better new alpha value compared to the initial design, and also they perform better in terms of the relative D efficiency compared to the initial design, that is OUCM, for all the cases, all the factors. Moving on to the result for the generalized case deviation, it was observed that the OUCM performed better for the constant, linear, and bilinear terms with the least generalized scale deviation. Why the why other design now, like the central composite design, which is CCD, perform better in terms of the quadratic, that is the generalized scale deviation for the quadratic portion. And this actually applies to other factors, that is factor 4 to factor 11. We observe a similar trend that the OUCM, the new design that was constructed, performed better with least generalized scale deviation as compared to the other. So from this work, we then conclude that robust second order design, because the design we constructed as second order design, we conclude therefore that robust second order design were constructed as a variation of the initial second order OUCDs, and these the design structures of the OUCD and the OUCM were the same, except that the alpha values differ. So in general, the robust design had better Z efficiency value and generalized case deviation values than the corresponding OUCD, orthogonal array composite design, orthogonal array composite minimax loss designs, small composite design, and central composite design in most of the cases. And also, generally, the OUCM perform better in estimating all the parameters of the second order model, and thus it should be recommended when want to study a design that has missing values. Here we have the reference. I want to thank you all for listening and for your time. Thank you.